Okay, lesson 26 is a pretty brief lesson before the longer lesson, which is lesson 27, but this is just an introduction to parametric equations so that we can use them for a really fun lesson next time, which is polar coordinates. That's when you can graph really crazy things on your calculator, like flowers and infinity signs and so on. So it says, suppose we're going to throw a rock straight in the air with a velocity of 35 feet per second. So if we didn't have gravity, when you throw the rock straight up, it's never going to fall down, and it's just going to continue going up and up and up and up. So after 1 second, it would be at 35 feet. After 2 seconds, it'd be at 70 feet. After 3, it'd be at 105, 140, 175, and it would just go off forever and ever, getting bigger and bigger and bigger. Okay, so since we have gravity, obviously it comes back down, so we want to know how gravity affects this. All right, so with gravity figured in, the height of the object ends up being h of t equals 35t minus 1/2 times 32 t squared. Okay, the reason we have the number 32 in there is because negative 32 feet per second squared is our gravity. Okay, so yes, in the equation, it doesn't have negative 32, it ends up being negative 16. There's some calculus involved, which involves the 1/2 and the t squared. But basically, so if we're doing this and we do have gravity and we're throwing it from the ground and up, now when we find it, we get 19 and then 6, and then all of a sudden we have negative values. So negative 39, negative 116, and so on. So what this means is now we've hit the ground between, let's see, 2 and 3 seconds. And you could try to estimate it a little bit better by plugging in like 2.5 or 2.3 or something like that to figure out exactly when it's hitting the ground. Okay. So basically, if you want a height equation, you might have seen the height equation before, h of t, and it involves gravity. So it's negative 16t squared because of the negative 1/2 times 32 that we had before, plus v sub o is our initial velocity times t plus whatever height h sub o we have. So v sub o and h sub o stand for initial, so initial velocity and initial height. So in the first example, we had a height of 0. So now it says, now suppose that we don't throw the rock perfectly vertically. Instead, we throw it outwards at an angle of inclination of 30 degrees. With that same initial velocity. So here's where we're going to mark the 35 feet per second now. So what happens is we have a vertical component to our velocity and we have a horizontal component to our velocity. So we call this Vy and Vx. Okay, and if we want to find Vy and Vx, we use SOHCAHTOA. So we say sine of 30 degrees equals opposite, which was the vertical component, over 35, the hypotenuse. So we get Vy equals sine of 30 degrees times 35, which ends up being 1/2 times 35, so 17.5. And then likewise, if we want to find the v sub x, so the horizontal component, we do cosine of 30 degrees equals Vy over 35. So that one's going to be the root 3 over 2 times 35, which isn't as nice as the 17.5. So it works out to be like 28 point, that seems weird. Cosine of 30, root 3 over 2. Oh yeah, that's right. So 28.670 feet per second. Okay, so basically what it means is it's going a little bit faster horizontally than it is going vertically because we're throwing it more horizontal than we are vertical. Okay, so then the next little bit says the height, y of t then, ends up involving gravity because, you know, height, as you throw up, it's going to come down, right? So it involves gravity and it involves that, that vertical component of our velocity. So it ends up being, so 35 times sine of 30 times t, and then minus our 16, well, let me write it as 1/2 of 32. So minus the 1/2 of 32 t squared. So it simplifies to 17.5t minus 16t squared. But the horizontal distance doesn't involve gravity. If you're going to throw it out at a rate of 28.670 feet per second, every single second you're going to gain that much, gain that much, gain that much. So the horizontal distance, like I said, doesn't involve gravity. It's just that 28.670 t. Or maybe I could write it more precisely by doing cosine of 30 times 35t. Okay, so part B says, find when the ball hits the ground. How far has it traveled horizontally at this time? So when the ball hits the ground, that means that we want our y of t to equal 0. So we solve our equation. So we say 17.5t minus 16t squared. We can pull out a GCF of t. If we had an initial height in this problem, what we would have to do is we would have to use quadratic formula. So we get t equals 0, and we have 17.5 minus 16t equals 0. So I have negative 17.5 when I subtract it over, dividing by 16, and I get t equals 1.09375. So that's how long it takes to hit the ground. The t equals 0 was just where we started. It was already on the ground where we started. And then the second part of the question says, how far has it traveled horizontally at this time? So now we plug it into the second formula. So we do cosine of 30 times 35 times our answer to get its horizontal distance. I really should say x of 1.09375 equals that. Okay, so we get 5.905 feet. Okay, and then the last question says, when does the ball reach its maximum height? So as you know, the ball is going to go up and then it's going to come down. We said it hits the ground at 1.09375 seconds. So it actually reaches its maximum height directly between there. And this is because we didn't throw it from like the top of a cliff or the top of the building or anything like that. In those cases, you wouldn't be able to take exactly half. But since we're throwing it from the ground and then back up, it is directly in the center. If we didn't do that, we could use our calculator to graph and find a maximum because it's a parabola. And or you could use t equals negative b over 2a, like you learned from Algebra 2. So if I do half of the 1.09375, I get, oops, I erased it. I get t equals 0.546875. So we'll say about 0.547 seconds. All right, so let's talk about graphing parametric equations. Okay, so for the first example, it says sketch the curve given by x equals t squared plus 4 and y equals t over 2. So we just did an example of something that involved a parametric equation. So we found the x component and we found the y component by using two separate equations involving t. Okay, so this is exactly the same. So we can set up kind of like a t-table, but for the t-table, we actually have three partitions. So we're going to have t, x, and then y. So maybe for x, I'll write what the equation is so you can see. So x is equal to t squared plus 4, and y is equal to t over 2. Okay, and it says I want to plug in t values between -2 and 2. So I can plug in decimals, but I'm just going to go ahead and do -2, -1, 0, 1, and 2. And hopefully that's enough information to see what our graph looks like. So when I plug in -2, I get 8. When I plug in -1, I get 5. And then I have 4, 5, and 8. And when I plug in to the y equation, I get -1, -1/2, 0, 1/2, and 1. So if I graph my x and my y, what I'm graphing are these points. So it's really like 8, -1, 5, -1/2, and so on. Okay, so the t was just used to find them. I don't actually graph a t. So I have 8, -1, 1, 2, 3, 4, 5, 6, 7, 8, -1. Then I have 5, -1/2. And then I have 4, 0. And then I have 5, 1/2. And then I have 8, 1. So this is what my graph looks like. Okay, so it is a sideways parabola. So now it says eliminate the parameter to write a rectangular equation. So whenever you see a rectangular equation, that's an equation with x's and y's. So the way we eliminate a parameter is we solve one equation for t. So looking at my two equations, I have x equals t squared plus 4, and I have y equals t over 2. So my obvious choice for solving for t is the second one. It is much easier. So I get t equals 2y. And then I replace my t with 2y in the other equation. So I get x equals 2y squared plus 4. So I get x equals 4y squared plus 4, which we know is a sideways parabola. Now part C says use your calculator to verify your result. Make sure you check the window. Okay, so our window we said had to be between -2 and 2. Okay, so if you notice we have -2 to 2 right there. So we can actually graph parametric equations in our graphing calculator. So I'm going to use my little Wabbit app. Okay, and I want to go to mode. Whoops, maybe it's not going to work here. File, new. Now, of course, it's huge. There we go. Okay, so I'm going to go to mode, and I want to change it to parametric. So, oh, apparently I have to arrow over, and okay, so I hit enter. So I have parametric. All right, and I am going to go to y equals now. And when I do, you notice that I have an x and I have a y. Okay, so for x, I want to put the t squared plus 4. So when I hit my x, t, theta, n, it's now automatically going to give me t's. So I have t squared plus 4. And then under my y, I want to put, what was it, t over 2. So I'm going to do t divided by 2. Now, what you have to do with parametric equations is you always need to specify what your t's are going from. So I want my lowest t value to be -2, and I want my highest t value to be 2. Okay, and this t step, you don't really need to adjust very often. It's just going to tell you exactly how many, like it's going to say, I'm going to start with -2, and then I'm going to add 0.1308, whatever, to it before I plug in the next value. So what your calculator is doing is basically like a t-table. It's just doing it very, very quickly as it's graphing. Okay, so basically if you have this being very tiny, like if you had 0.00001, it's going to take forever for your graph to work. Okay, so now I hit graph, and I have that graph right there. Okay, you could hit zoom, and you could do maybe like a Z box if you want to see it, and hit enter. And the Z box is kind of cool because you're going to arrow over to where you want your first corner of your box to be. So I'm just hitting my cursor and I hit enter, and then I can arrow over. So I'm arrowing over this whole time, and then I want to arrow down, right? And when I do that, it's giving me this graph. So basically, on my graph, I actually made a little tiny mistake. I shouldn't have arrows on the end of here because my graph needs to end when t is equal to -2 and 2. So going back here, what I have to do is I have to stop my parabola. So it should stop right there and right there, okay? Because it's only picking t values between those two things. So that's why I said make sure that you check your window, make sure you're checking your domain originally. Okay, so number 2 says graph x equals sine of t and y equals sine of 2t from 0 to 2 pi on your graphing calculator. So we're going to go ahead and do that one as well. So I'm going to go back to my y equals, and I'm going to put sine of t. Well, let me clear it out before I even begin. So sine of t. And then I want to clear the second one. And I want to do sine of 2t. Okay, and now I need to hit mode first on this because I need it to be in degrees. Not degrees, sorry, radians. It was already in radians. Okay, so I need it to be in radians. And then I want to hit my window. And I want my window to go from 0 to 2 pi. Let's see, pi, where's my pi? Second pi. All right, and we're going to go ahead and try to hit enter with this and graph it. And I noticed that I'm in kind of a weird window from when I zoomed in before. So I'm going to do zoom, and I'm going to hit my standard window, so 6. Okay, and it takes me to my standard window. And it gives me this cute little infinity sign. Okay, and that infinity sign we're going to talk about a lot in the next section. It's called a lemniscate. So if you graph this, it looks like that. And that is the shape that we get. Okay, so we're going to have lots of really crazy shapes. Like I said, in the next section, we're going to have things like flowers, right? We're going to have crazy graphs, which will be a lot of fun for you guys. All right, so what if we have something that has like natural log? Oh wait, I did say, oh yeah. So sketch the curve, so I guess I have one more before that. So sketch the curve represented by the parametric equations, then eliminate the parameter to write the rectangular equation. So I don't want you guys to be totally dependent on your calculator for these, because sometimes your calculator can be a little misleading. So on this one, I don't say what t should be between. So when I graph it, so if I have, go to my window, or sorry, not my window, my y equals, and what do I have? 2 times t plus 1. And then the other one is 3 minus t. Sorry, it takes me forever to type these in. Okay, and then I hit graph. Okay, it looks like part of a line, but it's actually not part of a line. It's actually the entire line. So the way that we can see that is under our window, our t-min, let's make, I don't know, just negative 20 and 20, let's say. Or you could do negative 10 to 10. And when you hit graph, it will take a little bit, but you see the whole line, okay? So really t is unbounded. There's not like it doesn't say from 0 to 2 pi or anything, so really it's from like negative infinity to infinity. But if you put in like negative 5,000 to 5,000, your calculator is probably going to give you an error, just because it's like trying to calculate way too many points, and it takes way too long, okay? So let's see why this one is in line and exactly what line it is. So we're going to eliminate the parameter by solving one of the equations for t. So let's say I add the t over and subtract the y. I have t equals 3 minus y. And I plug into the second equation. So I have 3 minus y plus 1. So I get 2 times 4 minus y. So I get 8 minus 2y equals x. Let's say I want to solve for y, so I'm going to have x minus 8 over negative 2 equals y. So y is negative 1/2 x plus 4. So we know that that is the graph with y-intercept of 4, slope of negative 1/2. So we'll end up crossing at 8, and it will look like that. Okay, so I go down 1, right 2, down 1, right 2. And that is exactly the graph that had been drawn, or the thing we found on the calculator. So that's correct. All right, but you can have weird things too. So like I said, maybe I have something that involves natural log, and then 2t squared. And this one's kind of weird, because it's like, well, which one should we solve for? We could solve for the t here, but we'd have t equals plus or minus the square root, and that's kind of messy. So we actually don't want to do that. So what I'm going to do here is I'm going to solve for t in the first equation. So I'm going to do, remember, natural log is just log base e. So when I switch forms, I have e raised to the x equals 2t. So e to the x over 2 is equal to t. So when I plug in my second equation, I have 2, and then I have e to the x over 2 squared. So I get 2 e to the 2x over 4, which is 1/2 e to the 2x. Okay, that is your rectangular equation. So you can graph using either the rectangular equation, or you could use the parametric. So we could do both if you wanted to check. So we're going to go to y equals. We're going to clear out and clear out. So when I go back up here, So I'm going to put in a natural log of 2t. Okay, and then I'm going to put in 2t squared for the other one. Okay, and I don't tell you what my t should be between, so we'll go ahead and hit graph and see what happens. Okay, and you can barely see it. If you need to zoom in, you can. So you could just hit 2 and zoom in and hit enter. Because you can't really tell if it was crossing the x-axis, but now you can. Okay, and that's exactly what 1/2 e to the 2x looks like. You can check by going back to your rectangular. You would just go to your mode and you would change your function. You would change it back to function notation instead of parametric equations. Okay, so then the very last example says use every multiple of pi over 4 on the interval 0 to 2 pi to make a guess at the rectangular equation for x equals cosine theta and y equals sine of theta. Okay, so this one takes a little bit of time. So you have t, you have x equals cosine theta, and you have y equals sine of theta. And so I told you to use every multiple of pi over 4. So I'm going to have 0, pi over 4, pi over 2, 3 pi over 4, and pi. And then I'm going to have 5 pi over 4, 6 pi over 4 is 3 pi over 2, 7 pi over 4, and 2 pi. And you can think about the unit circle as you're doing this. So you can think, okay, if I plug in 0 for theta, I get a cosine value of 1, a sine value of 0. If I have pi over 4, I'm going to have root 2 over 2 and root 2 over 2. And then I'm going to have 0 and 1. And then I'm going to have negative root 2 over 2 and root 2 over 2. And then I'm going to have negative 1 and 0, and so on. So I get negative root 2 over 2, negative root 2 over 2, 0, negative 1, root 2 over 2, negative root 2 over 2, and 1 comma 0. So as you're sketching this out, I think you'll realize what you have. We have 1, 0, then we have root 2 over 2, comma root 2 over 2, then we have 0, 1. We have negative root 2 over 2, comma root 2 over 2, and then we have negative 1, 0. So as you can see, what we're doing is we're actually just sketching the unit circle, right? So if we connect all of our dots, we get a circle. So that circle, if you talk about rectangular coordinates, it's just the circle centered at 0, 0 with a radius of 1. So it's x squared plus y squared equals 1. Well, that's our equation of the unit circle. That's it. So why is that? Because we know that on the unit circle, the x value is cosine theta and the y value is sine theta. And even further, we know that sine squared theta plus cosine squared theta from our identity chapter is equal to 1, right? So it all comes together, it all works. So if you have x equals cosine theta and y equals sine theta, that's actually the parametric equation for the unit circle. So we'll be doing more with thetas in the next section. The next section is a little bit longer, so hopefully you enjoy this short homework assignment. But the next one, lesson 27, like I said, is a little bit longer. All right, thanks.